Thank you, everybody, for coming this evening. My name is Dr. Keith Crumpy. I'm the chair of the chemistry department here at UNCA, and we all of us in the chemistry department really appreciate you coming out this evening and helping us celebrate this event to honor such a very wonderful person. Some of you were here at this afternoon's lecture, and we appreciate you coming back. If you weren't here this afternoon and you are new to the Squibb lecture series, let me just briefly describe for you why we've all gathered these last couple of days. This gentleman sitting over here in the middle between these two people in the gray suit is Dr. S. Dexter Squibb. He is... I personally owe a tremendous debt of appreciation to him. He was the department chair who hired me here 14 years ago. So I wouldn't be here today speaking in front of you if it hadn't been for him. So I owe him a tremendous amount. But beyond hiring me, which probably won't go down as one of his greatest achievements, Dexter was the very first chair of the chemistry department at UNCA when we began, and he maintained that position and moved this department from nothing up into a very substantial, very well-recognized and well-respected department, and led the department for 30 years. I've only been doing it for 2.5 years, and I'm not quite sure how he manages to do it, but whatever he's taking, I need some. So Dexter, thank you for that. Thank you for getting us to where we are today. When Dexter retired, now 11 years ago, I believe it was, in the department, we tried to figure out what could we do to recognize Dexter's great achievements, and there are many of them, but probably more than anything else, Dexter needs to be recognized, and we appreciate everything he did in the context of teaching. He's a consummate educator. Students for years have appreciated what he has done for them, what he has taught them. Even though I was never an official student of his, learned a tremendous amount from him in the context of chemistry, in the context of being an administrator, in the context of being a member of a department and a member of an institution. So we all owe Dexter a tremendous amount for that. And so we created the S. Dexter Squibb lecture series. And what I'm going to do right now is I have the honor of introducing a former colleague of mine, Professor Emeritus Leo Bars, who just recently retired but still is an active member of the department. And Dr. Bars is going to introduce Kathy Middlecamp to you.
Good evening, everyone. A very warm welcome to all of you. As Keith has already indicated, it is my pleasure to introduce our speaker this year in the 8th annual Dexter Squibb series. Our speaker is Catherine Middlecamp from the University of Wisconsin. Kathy, as she prefers to be called generally, I believe. Kathy is a chemical education specialist. She is the director of the Chemistry Learning Institute at the University of Wisconsin in Madison. And she is also a distinguished associate member of the chemistry department. What could be more appropriate than to have an educational specialist giving the keynote lecture in a series in which we honor a man, Dexter Squibb, who has made education his lifelong pursuit. In addition, Dexter was an exceptionally fine teacher. I think that's a wonderful choice of speaker, and I certainly commend the organizers of this series, John Stevens and Keith Crumpy, for bringing Professor Middlecamp to this series. In the way of academic background, Kathy is a Phi Beta Kappa graduate of Cornell University in 1972. I might add that she had the distinct privilege and honor of taking general chemistry from Nobel laureate Roald Hoffman. Roald Hoffman is one of my personal heroes, and I'm sure that he had a great deal of influence on her subsequent professional life. She was a Danforth winner and did her graduate work at the University of Wisconsin, earning a PhD in 1976 in the field of, you guessed it, inorganic chemistry. Kathy also holds a master's degree from the University of Wisconsin in counseling psychology and counselor education. She regularly teaches the Chemistry in Context course, which you will hear a lot about, but for those of you who might not be in the know, Chemistry in Context is a course designed specifically for liberal art or for non-science majors. Kathy also teaches a course called Environmental Chemistry and Ethnicity. For those of you interested in diversive intensives, let me repeat that title. Environmental Chemistry and Ethnicity. In addition, she teaches regularly in the Integrated Liberal Studies program at UW. Over the past 25 years, she has designed, supervised, and taught in a number of programs in which students underrepresented in science are the principal constituents. She has also taught a graduate level course in teaching how to teach general chemistry. She has approximately 40 publications, largely in the area of chemical education. And I do want to mention that she is the co-author for the 3rd, 4th, and 5th editions of Chemistry in Context, and she is also on the staff as a co-author for the 6th edition of that wonderful book. Kathy has been the recipient of numerous awards and honors. However, I'm only going to mention a couple of those in the interest of time. In 2000, she was awarded the Pharmacia Award for Excellence in Teaching of Chemistry. In 2002, she was the recipient of the Women Chemists Committee of the American Chemical Society Regional Award for Diversity. In 2003, she was elected a fellow to the AAAS and the Association for Women in Science, and that year she was also awarded the Alliant Energy Unterkofler Excellence in Teaching Award. And as Keith mentioned, just recently it was announced in the Chemical and Engineering News that Kathy Middlecamp is the 2006 winner of the ACS Award for encouraging women into careers in the chemical sciences. In the past 2 days, I've learned 3 additional things about Kathy Middlecamp. One, she holds a black belt in Aikido, a Japanese martial art. Secondly, she is an avid and very strong hiker, capable of hiking me into the ground. And thirdly, she is a delightful, charming individual. Please help me welcome Kathy Middlecamp as she presents Uranium and You.
And can you make the... We got to let the back row have a chance to go to sleep. Can you turn down the lights a little? Yeah, that's better. And even a little, it's awfully bright in here. Just a little bit, take the edge off it. Okay, is that enough? How's that? I mean, we did the after lunch talk. Now it's the after dinner talk. How's that do for you? Need a little brighter? Okay. Where'd he go? I was just looking for you. He almost told the truth. He was leading me up the mountain. All right. Thank you for coming back for part 2. How many of you were here at lunchtime? Oh, good. All right. I'll put some of you to work in a little bit. It's a slightly different talk, and it's meant for the public, although I'm glad there's all sorts of different members of the public here. For those of that you weren't here, I hail from Wisconsin, and there really are 24 Universities of Wisconsin, and I get that one. I want to go back to where we were earlier at lunchtime. We weren't there. Long, long ago on a planet far, far away. Is this going to get better? We're going back to Alaska for a different reason this time. And that really was Fairbanks in December a few years ago. And it looked most of the day more like this, where the sun crept up a little bit and was down. It was a balmy day. It was in the plus numbers. And the picture I have here is that while I was giving some lectures there, I had been asked to go into the public schools. And this was a charter school for the Native Alaskans. This is not a picture of the students in the school. I don't put up pictures of people I take places without their permission, and I forgot to ask their permission. But this was a group I did have permission to photograph, and they look kind of like the ones I was teaching, so I hope you would mind if I just put in the picture I could put, and I don't have any actual pictures of the school. But I did have 20 students, and we had a grand time talking about uranium. And what I started the conversation was, I mean, the teacher had said that they had learned quite a bit about radioactivity, and I could feel free to jump right in and see what they knew. So I said, let's do that. And I said, okay, guys, in this classroom, what's radioactive? And then I looked at them for a minute and said, you know, you're a pretty lousy detector of radiation. And they're looking at me. I said, you really need one of these things to help you. So what do I have up here? Geiger counters, right. This one's mine. I've got it down here, and you may be listening that it's chirping away a little bit. It does that. The one at the bottom is sort of an antique. That's what the prospectors used in the West when they were looking for mineral deposits. And that one was from one of the national labs, and we have kind of the same vintage right here. Geiger counters come in all shapes and forms, but somehow they do what people do not do very well, which is detect radioactivity. Again, you're a pretty rotten detector of radioactivity. You need some help. So I said to the students, okay, what's radioactive in the room? And without missing a beat, one of the students said, the lights. I said, okay. I gave him the Geiger counter, and he climbed up on whatever and reached up to the lights. He said, no, they're not radioactive. Okay. Now, the lights, at least in Alaska, were not radioactive. Now, this is a group I do have permission, very happy permission. I was working with a group of teachers in Chicago, and they had just finished a week on radioactivity, and out of curiosity, I thought I'd ask them the same question. I said, well, what in the room's radioactive? I gave them a Geiger counter, and the first thing they said was the lights. I thought, well, we got a pattern here. Now, they did not climb up on the tables. Rather, I climbed up on the desk, and they were filming it there just like they were filming it here. So what I want to show you is the film clip of me on the desk. You'll see a little bit of climbing in here. But what I want you to listen to is their reactions to what I was doing and whether or not they still thought the lights were radioactive after I climbed up on the desk. So the same question, was it the lights?
Yeah, little. It's clicking more than before. Here and there. Nothing going on there.
Oh, now I got to get down. Thank you. I got that on film. As you'll see later, there's a reason I'm wearing the same clothes now that I wore then. I really have changed them since then. But it dawned on me that this question about the lights maybe had something to it in that people thought that would be the first place in the room to look. And the students then, when they didn't find the lights, they had not given up yet. They took the Geiger counter and went right over to the outlets and said, how about the electrical outlets? Those are radioactive. And you know the punchline here. No, the outlets were not radioactive. And, you know, I was thinking, what are they thinking? So I had to ask them. And they said, don't light bulbs give off radiation? And I said, oh. Well, you know, there's radiation, and we might take a minute to go through this. And I also assume if people in Alaska were asking about light bulbs and outlets, and people in Chicago were convinced, even when I was standing up, because then we had to have a conversation of why the Geiger counter clicks, even though it's not particularly near anything. I mean, I can really make it click if I want, and we'll do that in a bit. So we talked a little about background radioactivity. But one way in which we use the word radiation is to talk about electromagnetic radiation. Some of you, this is very familiar to. And the other way we use to talk about radiation is nuclear radiation. And just to make things a little more complicated, some of the electromagnetic radiation, like gamma rays, actually is nuclear radiation. And to make things even worse, at this point, we often refer to it as ionizing radiation, not nuclear radiation. So there is a bit of confusion in the language, which brings me back to a principle we were talking about earlier today, which is context determines whether you're talking about radiation or you're talking about radiation. And today I want to talk about nuclear radiation, which does include some electromagnetic radiation, which is gamma rays. So we kind of sorted our way through this. And it's a reasonable thing to be confused about. Scientists sometimes use words in different ways. The one that's getting all the press today is the word theory. There's theory, and then there's theory with a capital T. I'm not going to go into that one. So I said to the students, let's make a list of what's radioactive in the room. And we had convinced ourselves it wasn't the lights and it wasn't the outlets. So the next thing the teenage boy does is he immediately takes the Geiger counter over to the head of his girlfriend and checks her out sort of head to toe. And I'm just going, oh, this is what's going on. We determined that she was not radioactive. We determined that the ice cream, we went through a whole list of things with the Geiger counter. And finally I said, okay, gang, what do you know about radioactivity? And they did come up with this one, which now, from the folks who were here earlier or from anywhere else, where does the radon come from in our atmosphere, in this lecture hall? Where's the radon from? Yeah, ultimately it's from uranium. And I had this same conversation with my own students in my chemistry and context course. This is opening day, and I've got not the nice 90 of you I have here, but I have 290 students. And I asked them the question, are you breathing radon as you're in the lecture hall? Would I put you in a lecture hall where you're breathing radon? And I would, because I can't do anything about it. Yes, there's radon. But we track our way through this conversation. They're a little miffed that I would put them in a lecture hall that has radon in it. But I generate for them, with them, the same thing we were looking at earlier. That indeed, if there's uranium, there's radon. Now, does that mean there's uranium in the lecture hall that's making the radon in the lecture hall? We'll come back to that. Because I immediately were suspicious if this makes that, then that ought to be here too. So we will come back to that. Bottom line, there is uranium in the soils and everything else under the lecture hall and under the buildings and under whatever, and that is, by and large, the source of the atmospheric radon, but we're not quite to that yet. So then I asked the students up in Alaska and the teachers in Chicago, what else is radioactive? And at this point, they had caught on, and their answer to me was, well, all the stuff you brought is radioactive. We know where it is. It's all sitting on the table in the front of the room, and that shut me up. And then I thought, well, it's probably time to have a conversation about what I brought. And you may be wondering, I notice there aren't too many of you in the front row. Generally a good idea in a chemistry course. I'd like to talk a little bit about safety, and isn't indeed where Lee is sitting, the hot seat, and might he want to move to the back or not? All right. Well, this is a shot of pure uranium in the metallic form. If you mine it, I do have some uranium ores here, and if you do your work, here for the camera, and get it out of the ground, you can refine uranium out of uranium ore just like you can get aluminum out or iron out or anything else out. But much more commonly, uranium on our planet is found in one or more different kinds of ores. There's hundreds of ores that contain uranium. That's just one, and I did have a big piece, and I decided for a variety of reasons it wasn't coming with me on the airlines here. I'll get to the airlines in a minute. Well, okay, I've already confessed that I've got uranium ore here, and there's maybe a couple other things. It just might be up here. How dangerous caution, radioactive materials. What should we be thinking here? Okay, multiple choice. Behind door A, B, or C? All right, let's start with B. How many for choice B? Okay, way to go, there's a voter. Choice A. Choice C. All right. Choice C is what I would vote for too. It's a loaded question. It's under most circumstances. If you have a ton of it and it's pure, you probably don't want to sit on it. But by and large, something I need to say about uranium for those of you that don't already know, it does come in 3 flavors on our planet. We call them isotopes. One of them is the predominant isotope, that's the U-238. Maybe one of the most fortunate things on our planet that middle one is not so abundant, because that's the one that fuels nuclear bombs. It also, in different amounts, fuels nuclear power plants. But it means it isn't all that easy to get your hand on. Our planet doesn't have that much. And if you look at those 3 numbers, they have one thing in common. They're big. The half-life is roughly an indication of how fast a radioactive substance is ticking. Now, they don't really tick. They don't really glow in the dark, although I'm going to make them glow in the dark in a minute. But that 4.5 billion years means that it takes, give or take, 4.5 billion years if I have this much uranium to have half as much after that period of time. Contrast that with an isotope like we were talking about radium this afternoon, with a half-life of 1,000 years. That one's ticking a lot faster. So why is uranium weakly radioactive? Well, part of it is that it's not decaying very quickly in comparison to it. So that's one reason. Now, I'm still holding on to it. I've still got it on the table. I haven't quite explained why one might not be worrying even where Lee is sitting. This slide is intentionally blank. And I did it that way so you could keep your eye on the PowerPoint and its cute little things. Well, I picked this one because what does it look like? Well, it looks a little like an atom, and I want to put the nucleus in there for you. Might as well make use of the slide. My best imitation of what a uranium atom does when it undergoes radioactive decay is just this. It shoots out an alpha particle, 2 protons, 2 neutrons. Kind of a big particle, has a +2 charge, does a couple other things we won't get into, but then changes its identity into thorium. And you remember, those of you who are here, uranium goes to thorium goes to protactinium, goes back to uranium, goes to thorium again, goes to radium, goes to radon, and eventually ends on lead. And if you like bookkeeping, we can do it this way, that a big nucleus spits out a little particle, turns into something else, and that is what this sample is doing as we sit here. It is decaying, and I think the calculation I did was roughly a couple of decays every second. I may not be able to get them on the counter, but the amount I thought was in here is not very much. And it's alpha decay, and okay, there's the whole food chain, uranium's food chain. I didn't say that. Alpha, with apologies to the radiochemists in here. The thing about alpha particles is they don't get very far. In particular, if I'm holding this here, they're not making it to you. They're getting stopped by the air. Now, why am I holding it then? There's no air between my fingers and this uranium rock. Aha, it's telling us the answer. You know what's in your skin? Your fingers are covered with a layer of dead skin cells. That's how our skin works. At least the fingers have calluses. That's also plenty to stop the alpha particle before it gets into my fingers. And if I wanted to demonstrate, where's my real Geiger counter? I can put this up close and get a little bit of noise out of the thing. That's pretty good. But the minute I back it away, let me give it to you. Are you in range here? He's approaching. Okay, so we're talking an inch or 2 at most. And I think the front row, we're not going to poison the distinguished guests, at least not yet. We have a couple other things planned for them later in the evening. Okay, so in terms of safety, I am going to be passing some things around. The one thing I would suggest is if you happen to be pregnant or think you might be pregnant, I wouldn't go near anything radioactive that anybody's passing around, no matter what anybody says if it's safe or not. It's just common sense. I also probably wouldn't take some of these things and put them in your pockets. There's reasons men might not want to put things in their pockets. But short of that, I think I've demonstrated to you that it's not particularly radioactive to start with. This is about a 1% ore. It's also giving off alpha particles that don't get very far, and your skin is going to protect you for anything. I wouldn't then put your fingers in your mouth. So saying that's probably our safety lecture. And I want to now take these two pieces of ore, and I'm going to put them in the suitcase here. When I was in New Mexico on site doing quite a bit of research for the course that I do teach, which is Uranium and American Indians, it's the story of the Navajo uranium miners. We'll get there momentarily. My Navajo colleague and I went out to the reservation and started looking for the uranium, and we finally found it, and we got a whole bag of this stuff. And in my carry-on luggage, I put it, because I needed to carry it back so all my students and everybody could see it. And what you just saw and what I know and what you know is, should the safety people be able to detect the uranium outside of the suitcase? No, they're x-raying through it to see what's in it. They will see that my suitcase had a fair number of rocks, and they might have been wondering what I was carrying. But can these x-ray detectors detect alpha particles coming out of that suitcase? So I was thank you, I agree. Everything I know about uranium should be no problem. They're going to see a strange lady carrying a bunch of rocks, but probably people have done that before in New Mexico. So look at the date. This is how many months after what? And I'm thinking, they cannot know that I'm bringing all my uranium back. I had to get it back. I mean, one of my students could say, I had uranium, but I was afraid to bring it back through the airport. No, I was going to carry all my rocks back, and I actually carried them here too. So I had my suitcase. I got through TSA, the regular security. I was a little bit nervous about the whole thing, but I got through, and as far as I could see, they didn't bat an eye at my suitcase. And then I got to the gate, and I was going back through Minneapolis, flight out at 2:10, and I fly a lot, like some of you in here. I'm a platinum flyer, and the good news on some airlines, if you fly a whole lot, they give you the seats up front. They let you sit up there close to the pilot. So I was in seat 1A, and my colleague, Omi Baldwin, was in seat 1B. And what they did is they opened the jetway, and they called for first-class boarding. So I took my rollerboard, and Omi was with me and my friend, and I went tooling down the jetway, and I got a third of the way down the jetway, and the voice comes from the top of the jetway, passenger middle camp halt. Oh, no. And then the Northwest gate agent comes running down the jetway and says to me, the FAA has denied your boarding. And I'm about to say, you can have the uranium, you can have my firstborn child, you can have anything, just let me get on the plane and go home. And then the next gate agent comes down and says to me, you have too many carry-on items. And Omi says quickly, it's true. They had just changed the rule. You used to be able to bring on 3 items in first class. They only could take 2. I had my purse. I had my pillow, because I like to carry my pillow on the plane. I had my shoulder bag, and I had my rollerboard, and I probably had my laptop. So I had my arms full of all the crap I carry on a plane. I'm a very happy flyer bringing my creature comforts. And Omi says to me, she's carrying my stuff. And then the gate agents got in an argument saying, you're hassling our premium passengers. And then they were saying the FAA really is going to hold this flight. They are serious that you may not carry on your 3 items. They started fighting. We just started. We got on the plane. We hid all our stuff in the overhead bins. And did they know I was carrying uranium rocks? No. And I really knew this, but I was agitated, shall we say. So, end of the safety lecture. I believe that they would not care that I was carrying 1% ore. I carried a lot of rocks back, and I still have them. So in terms of the safety of the stuff we've got down front, they're alpha emitters, they're weakly radioactive, they're all household items, except for the 2 rocks that I put in the suitcase, and I will actually just put the suitcase and its rocks over here. So I will not be passing around the rocks, but all the rest of the stuff I brought is really household items for us to play with. So, is there uranium here that's producing all the radon? And that was the question I sort of danced by a little earlier. How about this one? Behind door A, door B, or door C? Okay, we'll go in order this time. Choice A. I love it when people really vote. Good. Choice B. Good, thank you. Okay, choice C. Of course, I don't know what these choices are. All right, let's go find out. Well, it's not just more abundant. Here's gold. And now I'll do uranium. So the difference between 3 or 4 parts per million and 3 or 4, let's see, tens, hundreds, thousands of a parts per million, it's a factor somewhere between 500 and 1,000 times more abundant in the surface of our Earth than gold, which surprises a lot of people, including me when I read it, which means that in general, looking at the rocks that you're going to find around, especially igneous rocks, uranium's all over the place on this planet. The rocks, the soils, the rivers, the oceans, it gets into everything. It also gets into building materials. This is a shot I took inside when they were ripping, periodically in the university, ripped apart the walls and do things, and I got to take a good look at the walls, and there's building materials. And if you want to look a little more specifically, the granite is the type of rock that is the big uranium source here. And going down through, bricks and dry board and wallboard are all having some amount of uranium in them. Well, what does that mean about what you're eating? It gets into everything, okay? Pumpkin pie, coming up soon. So uranium in U, if you wanted a number after all is said and done here to take home at the end of the day, 90 micrograms of U is uranium, not very much, a radioactive smidgen. Your backyard, though, if you start taking bigger volumes than U, all right, does your backyard, let's get the math here. 10 meters by 10 meters, this is a funny question because you notice the dimensions are in metric and the question is in English. Sorry about that. But you're bilingual, so meters by about a meter deep. A big plot. How much are we talking? Choice A? Choice B? Choice C? And a lot of people who haven't voted. It's just short of a pound. And part of this is because the uranium is all over the place in the soils and the subsoils and the rocks, the clays and the sands. And part of it is because if you look up there on uranium, it's one big fat heavy atom, which means that if you put them together in one, it doesn't take that many to weigh a lot if we want to go back into moles and stoichiometry. We'll get back to how heavy uranium is in a bit. The thing about uranium is most of it, if you want to mine it, is only in a couple of places on the planet, and it's Australia, by the way, that wins, having the best, yes, there you are, the best uranium to be found. But there is also some in the Ukraine, which we'll get back to momentarily. You notice in the United States, that shows in the middle, it looks like, what does that be? It's not where that is. It's in the Four Corners area, but I'm trying to think, where's the middle? Is that Kansas? Okay, all right. So in here, is your, I said there's radon in here. Is there uranium in this room, short of all the junk that I brought, that's producing some of the radon? And I want to say, yeah, there's a little bit. It's in the building materials, it's in the wall boards, it's in whatever we've got. I haven't quite taken apart your building yet to see what it's all, the slates and things. Sure. We're talking parts per million, but there's a little bit of it in here. And since uranium is around on our planet, people have discovered it, although they did not know it was radioactive, and they did not have a name for it back in '79. But this is the earliest reported date of when folks used uranium to make pretty glass, and they uncovered a piece in Italy. Long before the discovery of uranium itself, and then remember that map, let's see, I didn't put it here, where there's a little bit in the Ukraine. Well, Bohemia is modern-day Czechoslovakia. It's in that area. The miners there would take it and put it in the glass. And this is one that pitch blende was one of the ores. And the cover slide that I had on this talk is just a beautiful shot of this yellow-green uranium glass with maybe 1-2% uranium oxide used to make the pretty glass. I got that, putting it in context, that came from the museum up in Los Alamos. And there's a shot of it it was in a longer wall of some very cool radioactive displays. And if you ever get up to Los Alamos in New Mexico, it's a great museum to go to. In terms of beads, this was also taken from the Los Alamos Bradbury Museum. Those are sort of like Vaseline glass beads. They didn't call it that back then. Taken from the same shot. They had a Geiger counter there you could play with them on. Here's another beautiful set from a Japanese collector of the glass made in England. We made it in this country, depression glass. You may have seen it. You may own a piece of it. Another beautiful Japanese piece here. And I wanted to look at this one. I always wanted a piece of this glass myself. It's the only, to my knowledge, glass that, as we're going to see momentarily, fluoresces. And the best I could do was this little, you can buy these on, it's not eBay, there's a place that sells little uranium things. This is my little uranium dog. So that's a multi-$1,000 fish, and I have my $10 uranium dog. But I brought it here, and you can come up and play with it. But what I had just said, I'd like to demonstrate for you, that under UV light, uranium glass does fluoresce, and it's actually one of the things, yeah, go Keith, that makes it so desirable. We'll take it, okay, back to UV, there we go. Ultraviolet is slightly shorter wavelength, slightly higher energy than visible, and you are a lousy detector of it, just like you're a lousy detector of radioactivity. Your eyes cannot see UV. Now, we've got a black light here, which is what we often call the UV lights. You want to cut the lights in the, bye. Sorry, camera people, this is your, all right? And turn on there must be an on switch here before the lights go out entirely. On. Okay? Oh yeah, there we go, on. What you see is purple, but that's the part of the light you can see. The part you can't see is the UV, and I want to get it a little darker in here, okay? Yes, please. All right, so let's do a little bit of, first my dog. Okay, and I'll tip that, I really don't want to look at it. I don't want them to look at it either, good. There you see the fluorescence. It's taking in UV and it's giving back green, and of course you see the green. I've got this nice set of marbles here, which I will pass around to you in a minute. I've got a couple rocks, and things don't all, there's other things that uranium that fluoresce, and these are a couple of rocks and, well, minerals here. But they don't make the same beautiful clear glass that uranium does. Now, what else are you thinking? And what might you be wondering about my necklace? Well, should I be wearing it? Okay, is it radioactive? Well, is there anything else I need to play with while we got the lights off? These are kind of cool. This is fluoresces too. Anybody got a nice white? Just shine it out at them from, there we go, the cameraman. Sorry about this. You notice the shirt and the nice purple fluorescence there? Those are fabric brighteners. And we could have another whole talk. There's people over there are fluorescing very nicely their white clothes if you haven't spotted them. And let's get this off, lights on. Trouble about the dark is you can't see. There we go. Where's the thank you. The off switch. Oh, the necklace. The necklace. Well, it certainly is uranium. Come on, you can do better than that. That's a feeblest. Well, it's radioactive. Definitely radioactive. Now, where did I get these beads? The bead store. I'll give you a little known fact that bead store owners are not very happy if you go in their bead store with a Geiger counter, especially with it on and it starts clicking. But these are all available. This is about $75 worth of beads. The big ones here are Vaseline glass, and they're about $1 a bead. This is also a very heavy necklace, which is why I tend not to wear it. I actually will pass it around so you can see see why you wouldn't want to wear it too long. Here you go. Don't swallow the beads. So it was better to use a UV light in the bead store than a Geiger counter. You just trust me on this one. And if you have one of these little lights, turn off just a second again, just momentarily. You can sneak up on the beads in the bead store with this and find out for yourself if they're radioactive, all in the privacy of your own little hand without the owners knowing that you're checking out all their beads. Thank you. So let me pass around to you your very own test kits here. And I've got a little UV light in each one. And when they eventually come back, I have a present of, let's see, Joanne, I think I'll give you the marble, and I'll give you the UV light, Dexter, so that you can make her light shine. Okay, so here you go, and oh, we might as well send the dog out while we're at it here. And I'll send a UV light with it. I've got more. Here's another UV light with the dog. I'm going to leave the lights on this time, though. What do we got? Black light. And can you just snooch down on, there we go. And if you want to watch, your shirts do glow in the black lights. They put a brightener in there which takes in UV and gives back a blue light. And that's how you get from the whiter than white stuff in your wash. I mean, again, a story for another day. It's not uranium that's making your shirts glow purple. Promise. People have been using uranium for jewelry knowingly. And I snapped these two shots both in the Four Corners area in museums. Genuine uranium ore in your earrings and genuine uranium jewelry from Moab, Utah. The beads they sell nowadays, though, and I got a bracelet I made of them too, people don't know. The bead, I couldn't resist. At some point, I went to the bead store owner and let my Geiger counter make noise. I said, well, actually, they said, "What are you doing in my bead store?" I said, "I'm checking to see if your beads are radioactive." And she said, "What?" I said, "Yeah, well, the yellow in the glass is fluorescent, blah, 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 blah." She said, "What?" And I realized this was a conversation that wasn't going anywhere. But by and large, I've been to many, many bead stores. I've checked out a whole bunch of jewelry. There was somebody's necklace at lunch I was really eyeing that I wanted to put a black light on. Yes, there's a lot of things in our world that are radioactive because uranium is really pretty. In terms of this being a hazard, I wouldn't sleep with it under your pillow. I actually don't wear the uranium necklace that often because it's quite heavy. I also strung it so where it hits my neck, if I don't have a turtleneck, the beads aren't coming in contact with my skin. That's probably overkill. But to say the flip side of that, the uranium also does have in it thorium and protactinium and a little bit of radium. So it does have some more serious emitters in it. It's not pure uranium because you can't get pure uranium. There's another set, New Mexico Atomic Jewelry, lovely Pat Barrage of Fort Worth, Texas, who will reign at the Night in Paradise at the U.S. Servicemen Service Club. Blah, 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 blah. First atomic bomb test in New Mexico. That atomic cheese sharp really is not radioactive at all. They just named it atomic cheese, and I put it up because it's from Wisconsin. This piece they had out at the Trinity test site. They opened it to the public, and it was a gorgeous piece of jewelry that's uranium glass, but they wouldn't let me play with it with my Geiger counter, so I couldn't make it fluoresce. It just was that color. Now, glass is not the only thing that glitters, and folks found out that it makes a beautiful orange glaze as well. So, I mean, uranium has had a long history in making things pretty. I think you're all familiar with Fiesta ware. I went to your cafeteria for breakfast, and I actually liberated a set of the plates thinking this was as good a lookalikes as I would ever find for Fiestaware, but indeed the orange one is not radioactive. It doesn't serve your food hot for you. But sorry, you knew that was coming. But one of these plates is radioactive and one isn't. How would you know which is which? Does it glow in the dark? Does this fluoresce? Actually, no. Can you detect the radiation? Okay, take-home message of the talk, you are a lousy detector of radiation. We got through that one. So which one is it? Well, let's have a look here. The Fiestaware, lots of things were made in the 30s. By the way, the US government, combining with the Fiestaware company, pulled all the uranium out of the glazes. So that one of those is the modern-day tangerine color, and the other one of those really is radioactive. And you can see they made orange in 2 colors and 2 time periods with a break in the middle, which of course corresponds with the Manhattan Project and part of the Cold War years. They were not putting uranium in the glazes when it was going other places. So let's get out the Geiger counter. My goodness, I thought it was the other plate, but obviously it's not. This one? Okay. So, behind door A or behind door B? Okay, would you sleep with this under your pillow? I probably wouldn't either. Would I cook and eat off it? Probably. Well, people were. I've seen some uranium glass that is meant to contain, I've seen one in a lemon squeezer. Probably I wouldn't want to use a lemon squeezer one because the acidic fruits and things, whatever in it, may leach some of the uranium out. You don't want uranium inside you. We'll get to that momentarily. Going, again, I'm tracking, if you had noticed, we started with 79 AD, and we've gotten ourselves through a lot of pretty glassware. And in the late 30s, fission was discovered. That's the process of splitting only one of the isotopes, actually, of uranium, splitting a big one into a little one, neutron-induced. Germany during the war, Second World War this time, took over the uranium mines, which did not go unnoticed by our country in wondering whether Germany was going to build an atomic bomb. And in 42, they got 2 shots there of Los Alamos. One is the Fuller Lodge Ranch, which was eventually made into the big area in which the Manhattan Project did its work to put together the first 2, actually the first 3 atomic devices. And that's a sign leading up there, modern day. I don't know what expression one should put on one's face when being photographed by little man and little boy and fat man. The yellow one is the replica of the plutonium bomb that was dropped on Nagasaki, and the little one in front there was the uranium bomb that went on Hiroshima. I did have a student say, "Where's the original? Why are you looking at replica?" I am not one hardly ever to say that this is a stupid question, but that one did stop me in my tracks. It said, well, just think about it. I mean, I'm very open to, and that's, I believe, it's hard, really hard to track down who's got photos of what in the atomic age. I'm pretty sure that was the first fission bomb done with uranium. The one done at Alamogordo, the White Sands Missile Range, was a plutonium when they were testing before they went to Japan. So again, we're tracking through uranium's history, and we've ascertained a couple things about a couple things here. Let's see. Moving into the 50s, Patty Martinez, who was a Navajo Indian, you can read it there, Apa Martinez, a Navajo Indian, that is his land allotment, and he's the one who found the yellow rocks in the Four Corners area, which I had a suitcase full, and now you know that story. Going back here, this started the uranium boom in the American Southwest. And a lot of it then was being put into the military labs and military purposes. Some for reactors too. The reactors that we run in this country are largely enriched uranium. This was the first reactor. It's no longer in operation, but it did use enriched uranium. And I sort of fast forwarded through some stuff there because I'm not a nuclear power specialist. I do want to get back to this idea of radiation safety. I think I convinced you that, sitting in the front row, you are not at risk from these household items. I'm hoping you're feeling pretty confident that the things that went back out in the audience, you know, the little marbles, a little this, that, the beads, the necklace, it's very, it's 1% uranium. It's an alpha emitter. It doesn't have much in it. And I don't want to leave you with the impression that uranium is all well and good and not dangerous. Outside your body is an entirely different story from inside your body. And I'd like to finish up this talk and then again bring closure to it, getting back to the Alaska classroom, as to what the problems can be with uranium that you can get into. So it's weakly radioactive. It is an alpha emitter. Stop by your skin, stop by a little bit of air, stop by a piece of paper. There I have marked on the map the Four Corners area. And this is the context in which I teach a course with a Navajo colleague on uranium and the Navajo people. It's the story of how being uranium miners ended up poisoning with lung cancer not only the miners, but their families as well, and a good section of their land. I start this particular part of the course asking students to name the states that go in the Four Corners area. I have seen Texas as one of the Four Corners states. I have seen California as one of the Four Corners states. But starting in the upper left quadrant, what do we have there? Okay, and moving over to the Colorado. Texas? Right. So Arizona's in the bottom corner. The reservation that Omi is from, her first language is Navajo. She's up in the Chinle area in northeastern Arizona. And we went on a trip there. This was one of several that I was doing reconnaissance. We really wanted to find ourselves a uranium mine and have a look at it and take pictures and bring them back. And you know how we brought the rocks back. Let's see, that's the Shiprock, that's Monument Valley. And this is a road, that's Mount Taylor. It's one of the four sacred mountains. You may know the one, the San Francisco Peaks in Flagstaff, and there's one up in Colorado and one in northern New Mexico. That's Mount Taylor. Omi calls it by its name, Tzotl, and it's a volcanic mountain that erupted some millions of years ago. It's a gorgeous set of peaks, and we were out, this is reservation land, looking for the uranium mines. We knew that underneath Mount Taylor there runs an entire band of the ore. It's not particularly rich ore, but it was good enough, and it was within U.S. soil that we could do something with it. Okay, there we do have the four sacred mountains, and that bottom right star belongs to Mount Taylor. And here's the shot of Patty Martinez. He was right in that area. Haystack Mine, to go back to this slide for a moment, is just a little bit to the southeast of Mount Taylor. And that's where we were running around in a Jeep looking for the uranium mines. Patty Martinez had found them long before it. The finding of uranium set off a veritable boom in the area. That's a shot from one of the museums. If the Geiger counter clicked, they staked the claim. The mines were often a one-person, actually one-man operation. They called them dog holes, some of the mines. Here's another view where you literally crawled in, got the ore out with pick, put it in, and hauled it off. This is not high-tech mining, but they did remove a lot of ore that way. Some of the mines were surface mines that were much bigger. This was Moonlight Mine before it was reclaimed, and you can get some sense of the terrain, the size of the vehicles and the roads that are over there. That one's much bigger. Here's the Monument Valley district that I showed you the pictures of Monument Valley earlier. 90 acres running for 11 years, 12 years, let's see, 5 and 2 is 7, 12 years, sorry. And 54 mines there. This got reclaimed as well. And that's pretty low-grade ore, the same that I was taking through the airport. Now, how do you find something in the reservation? Well, just across the line to where the reservation starts, there's often a bar, and Omi and I went to the bar to ask directions. Well, the directions were all being asked in Navajo because the woman in the bar and Omi talked for a while, found that they were related, which is the first thing one would do, is introduce yourself, introduce your family, your clan, get connected. And then Omi said, well, I'd like to go see the uranium mines. Where are they? This is all in Navajo, so she translated it back to me. And they said, well, go this way, go that way, go this way, go that way, go this way, blah, blah, blah. And we trekked along through quite a bit of ice and snow. This was in December. It does get cold in New Mexico. And we came upon this thing. Now, I'm a bench chemist. And I looked at that, and I said, I think that's a mill, but I've never been up close in a mill before. And indeed, it was a uranium mill. And so Omi and I decided to go knock on the door and see who was home. And we met the security guards. They had a skeleton crew, and it was pretty clear to us in no way, shape, or form right after 9/11 were we getting anywhere near the uranium mill. And they turned us around and sent us home. I was not to be defeated, and so then I got on the phone to some of the geologists in New Mexico, and I just kept calling and calling and calling. I finally got a woman, she said, you need to talk to Terry Fletcher. He will give you a tour of the mill. Okay, so I told him I'm writing for the American Chemical Society, I do nuclear chemistry, I teach a course, blah, 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 blah. Can I come see your mill? He said, sure. So hard hats and whatever later, we got quite a view of actually the milling operation. This has all now been entirely reclaimed. We saw this thing on the horizon and thought, what is it? And that is a tailings pile. When they separate the ore out, the mine tailings are left. That is 700 feet high and 1/4 of a mile long. And that black stuff you see is clay on it. Let me give you the aerial view of the uranium mill that we were running around both in 9/11 and afterwards. I think I have a pointer here. Right there. Not very bright. Come on. That thing. Oh, it's backlit, that's why. Oh my. And now we get the cameraman, now we can get the front row. Okay, here we go. That thing, is it gonna poke a hole in it? No. Okay, that thing from the air is the mill. This thing here is the gray 700-foot mile, and what I'm trying to say is this mining is on a big scale. I kind of left my beakers and test tubes. And I'm going to say this to the folks who teach. Oh. Here. Thank you, Keith. I've done a lot of things for the first time here in North Carolina. I'll tell you about some of the others some other time. To do this kind of work where it's not only cross-cultural for me, but it's also out of my disciplinary box. You're right, I'm an inorganic chemist. I did nothing with uranium as a grad student. I certainly knew nothing about mining. But if I wanted to teach the story, I was going to have quite a few adventures, including in the airport, and needed to get out of my intellectual box to be able to bring this kind of information back. And I think you saw at the lunch talk, I had to do the same thing in Alaska. I want to say it's its own reward, is getting interested in stuff that you weren't trained to do, following it through, and then bringing it home and adding story upon story. Here is the tailings pile from the air. We didn't get to go in a balloon or anything. He had these pictures for us in the office. I would have loved to have gotten up in a little plane. This is now completely covered over. The clay is in there to seal the tailings in and keep the radon in. Again, you want to cap the tailings because they do have uranium and they are emitting radon, and put it back in the ground where it came from. By the way, they could not put the uranium back in the hole. Have you ever dug a hole in the garden and tried to get the dirt to go back in the hole it came out of? It just never seems to fit. The same is true with mining. You take tons and tons of rock out and you can't get it to go back into the earth. So that's where it ended up. And there's Terry Fletcher. And that he is very proud of his remediation job. People from all over the world come and see his work. One of the things that made it work so well is they get very little rainfall, so they had very little to worry about leaching of anything. And that's the mill site afterwards that he did personally, the remediation, and was very proud to give us a tour of it. Looking in the mine, that was sometimes the kind of jackhammer that people worked with, air hammer, not jackhammer. And imagine the amount of dust. They showed these boots in the mining museum, and Omi and I looked at each other and said, those are way too clean. So the dust on the boots came home with the miners. The uranium dust ended up all over them, in their lungs, in their family as it got taken home. The yellow cake was the product. It was the yellow dust, or in Navajo, the word is something like klitso. Klitso. Omi has worked on teaching me Navajo. I have not quite succeeded yet, but I'm working on it. So the yellow dust was the health hazard. Remember I said don't swallow the beads. I'm going to add to that, don't grind up the plates. Don't grind up the stuff and use it. It's fine in these gorgeous little marbles, and it's fine. I hope my necklace comes back. Who's wearing the necklace? Maybe nobody wants to be wearing the necklace. So to connect the dots to where we started the conversation, what is radioactive in the lecture hall? The answer the students gave, I think the answer you would give is radon is in here. Radon is a health hazard if there they are, I see them. The beads are coming back. Radon does get inhaled into your lungs, and if it happens to decay when it's in there, radon goes on, where are we, 86, to polonium, which is a solid and a little speck. It may stick in your lungs and then go from polonium all down the food chain to lead, successfully exposing right next to your tissues the radioactivity, the radiation, the alpha decay and the beta decay as well. So in the wrong place, like your lungs, both radon, too much radon, it can be a health hazard, and uranium dust can be an incredible health hazard because it generates radon in your lungs, which then goes and kicks out all that radiation. And the net result was lung cancer, although back in the 50s, both the healthcare system and our ability to diagnose it are nothing like they are today. Most people who get lung cancer still do die. And that was also true of the people who contacted on the reservation, the miners. Again, a story that connects with today. If you want to see the imitation of what radon does, it emits the same alpha particle, not particularly dangerous if it's not in your lungs. Forms polonium, and for those of you who would rather see a more formal-looking nuclear equation rather than Kathy's pictures, we can bookkeep this using the mass numbers and the atomic numbers. Hey, yes, turn the camera back there. Lateral view, that's person lying, I believe, on their back. The oral histories are fantastic of the people who were the miners. They were done both in Navajo and in English, and this is one of the original sources that I use in my course, is to read the stories of the people who were there. You have miners in this part of the country too. I believe you've got some of the oral histories of the people who did the mine. The difference perhaps between black lung disease and the yellow dust in the lungs was that the radioactivity was perhaps a little bit quicker to cause the mischief than the black lung disease. But the same types of stories go together here in that people are trying to make a living. And that was very true in the case of the miners as well. So we tell all stories of the people and what they were doing. This one's almost my last slide here. This is a hogan. That's a Navajo word for an octagonal house. What's interesting about this one is the EPA, Environmental Protection Agency, took this hogan down and dismantled it because it happened to have been built by the person with the tailings. And this was one of the most radioactive houses in the Southwest and got a lot of press for what it was and the high levels of radon in it. So it was not only the miners that got affected, but then the uranium came out of the earth. People used it as building materials just like we do here, but they're much lower in parts per million. But that particular hogan got taken down for extremely high levels of radon. In terms of the present, this note came through to me. I'm on a uranium active list where I get sent it. The Navajo Nation President Joe Shirley, April 30th, has banned on the reservation uranium mining and processing. 2 weeks ago, I got another notice, though, but they're looking at opening that back up. So it's something that has gone on, gone off, gone on, gone off, as is true with mining. It's boom and bust and boom and bust. So the story in telling this part is to say that this is not just the history of the 50s, but it connects right up to a real people living on a real land, building real houses today, and battling with the same real issues. Should we mine it, or should we leave it in the ground? Should somebody else mine it? What should we do? Science can provide part of the answers, but science can't provide all of the answers. It takes mixing everything in, too, to be able to come up with a decision. Well, what do we have here? Oh, yeah, I don't like to leave questions unanswered. Back to the school in Alaska, back to the teachers in Chicago. The question I asked them, well, what's radioactive in the room? And very astutely, they came up with this list. And they were most interested with number 2, which may have caught your interest as well. I did finish the list for them. You may know of potassium-40. It is as naturally occurring as uranium. And it's on our planet. About 1 out of every 10,000 potassium atoms is radioactive potassium-40. Now, what do you know about potassium that's different from what you know about uranium? Is potassium a good thing to eat, at least in the potassium ion form, an electrolyte? Yeah. What's a food that's got plenty of? Bananas. As I understand it, bananas have been causing the border stations that are trying to detect radioactivity smuggled into our country a bit of consternation in setting off the Geiger counters. Because bananas are naturally rich in potassium or naturally rich in potassium-40. Now, that does not mean that eating bananas is going to increase your amount of potassium radioactive, because you're constantly cycling potassium and other electrolytes in and out of your body. So don't go home worrying about eating bananas. They're a good thing to eat. Carbon-14, tritium. What's tritium? Radioactive hydrogen. Naturally occurring, not very much, a smidgen in our world. A little bit of fallout from the 60s is still with us, not much. The major isotopes had half-lives that were either short or 30 years. If you take 1950, we've gone through at least 2 half-lives. We're down to 25% of the amount that there was right at the time of the atmospheric testing. That's the best list I know of the radioactive substances, and I suppose the very last thing to say is this thing has been chirping away, and it's not all from radon. What's making it chirp? What? Just go silent when I talk about it. Come on. Yeah, there's one more source. Are cosmic rays radioactivity? Not in the sense that I've been talking about. And you remember the slide I put up? Not just radioactivity, but ionizing radiation. The story I tell students about cosmic rays is long, long ago on a solar system in a galaxy far, far away, the universe started spitting protons and some other things in our direction, and they're still arriving today. Some of them do get through the Earth's atmosphere. There you go, thank you. And they will set off the Geiger counter just like radon is. So that chirping there is probably from 2 things. One is a cosmic ray. One goes through your head about every 7 seconds. And the other one is from radon. It's around in here too. Okay, so quite a cast of characters here. My usual suspects at the American Chemical Society, all the people that have helped me write over the years and edit. The Sensor Project has helped fund minimally, at least get me interested in going in developing this course on uranium and American Indians. That's the subtitle of this course, Environmental Chemistry and Ethnicity. In a catalog, you have to give it a broader title than the specific topics. The UW Institute on Race and Ethnicity sent us twice down to the Four Corners area to take pictures. Ooh, that's Jim Marshall. He's the one who provided a couple of the slides of the elements. He's got a fascinating slide collection. Here are the 2 of the museums up in Los Alamos. If you ever get there, they got really cool stuff. And here's 2 of them down, one in Albuquerque and the Grants Mining Museum, where I actually brought my Geiger counter into the mining museum. I learned too that not only do bead stores not like Geiger counters, mining museums don't like Geiger counters. This is my colleague. She and I traveled a lot of roads together. And thank you all. And who's got the dog?
I know Kathy will be happy to answer some questions. Because of the videotaping that's going on, we need to use a microphone so they can pick up the questions. One way to do that would be for me to run around like a chicken with my head cut off trying to get you the microphones. What I might ask Kathy to do, if you don't mind, would be to repeat the question so that the folks could hear it. Let me make one comment and ask 2 quick questions to start it off. One, the comment is that some folks in the audience may remember this. A number of years ago, there were some stories in the local press about some housing developments in the upstate of South Carolina, and they were having problems with health problems because there's a substantial uranium deposit actually in the upstate of South Carolina. So this is not just a Four Corners issue. this
It's just
is right in our backyard as well. The two questions I had was, one, if uranium is such a, not very radioactive, to use that term, why was it the choice for some of the first nuclear weapons? And two, if you could talk to us about what we're seeing now in terms of the treatment of food with radiation.
Aha. A question out of left field, and I think you heard it. Let me ask who out here knows, yes, uranium is weakly radioactive. Why was it chosen to fuel the first, actually the second, atomic bomb? Okay, yes. So there's radioactivity and there's nuclear fission. Radioactivity is the alpha, betas, and gammas, and there's a couple other things too we haven't mentioned. Fission is the process of taking the big nucleus and splitting it with the release of energy. Actually, it's neutron-induced. Fission is the process that drove the weapons, drove the use of uranium, a fissionable fuel, for weapons. Same fissionable fuel, by the way, works equally well. Different conditions, different amount of enrichment in a nuclear power plant. But fission, I think the short answer is fission is different than radioactivity, and I bet he knew that. That was just a plant. Food irradiation. Anybody want to take a gander at that one? What do you know about it? Cobalt-60 is one of the ways it's done. Actually, it's a beta emitter, but it has a strong gamma ray. And there are also some other sources for food irradiation that are generated like electronically as opposed to using a radioactive source. What do you know about food irradiation? Why did they do it? Preservative. Okay. Preserving food a good idea? I said, yeah, it's a darn good idea. So does it make the food radioactive? That's a little trickier, but by and large, I want to say no, but there are some questions. Just like cooking food makes some products in it that are a byproduct of the cooking process, the carbonizes and whatever. There is some arguments, I believe, that putting radiation food can have some what's the word I want? There could be some radiolytic, that's the word I want, byproducts of the radiation passing through, the ionizing radiation producing H2O plus, and then reacting with other things. I'll give a quick answer. In my opinion, the diseases that can come from food that is ill-preserved far outweigh, the benefits far outweigh the risks, if you don't have some other ways to preserve the food. If you do have some other ways to preserve the food, then you have a choice. And I'm willing to let anybody jump in. I'm not an expert in food irradiation. Again, I would call this a classic risk-benefit analysis, and I would tend to say that the benefits outweigh the risks. Not that there are zero risks, but the benefits outweigh the risks. Cooking has its risks, too. Preserving hot dogs with nitrites has its risks. Sulfites, yes, certainly has risks, and some people are quite allergic to them. So much of food preservation. Putting it in the refrigerator has its risks, because if you forget it in there and then you eat it, you can get very, very sick. Anybody want to jump in on that one? I don't know if there's some people that have strong opinions about it, but you heard mine.
Matthew, what's the Navajo position on the mining? Because you showed a slide, it said the state policy or the federal policy was to stop mining. But the interesting issue to me is that, we can have federal policies, we can have science, but then people need to live and
Make a living.
make a living. So what's the Navajo?
There, to my knowledge, and I'm the second person in the lineup here that you should be asking, not the first. I mean, my colleague Omi would give us a better answer than I would. I would say it's like a lot of issues that the people are divided. It's not a clear voice. As I understand, when Tribal President Joe Shirley made the ban, there was a lot of discussion, both sides, and it was not a clear-cut issue to say no. And likewise, it's still now an issue whether to reopen it. So I don't believe there is one opinion, and that I would expect, in that you've got people, again, you've got risks and you've got benefits. I really like risk-benefit analysis. It doesn't have a single answer. And somebody in here may know more about that than I do. Okay, here and then there.
this is first one's a comment, for the longest time, I've wondered why the home inspector did a radon test.
I missed what,
Why the home inspector did a radon test.
yes.
And so now it makes it much more clear. Let's just say that you took your burrito, leftover burrito perhaps, that you had a leftover
Now he
burrito.
knows, now you know what I ate for lunch.
And you put it on the plate you thought was okay, and you decided to put it in the microwave to warm it up. Is there any risk in that?
Mixing microwaves with uranium glazes?
Sure.
I've never done the experiment, and I will go home and do the experiment so I can give you the empirical answer, but my guess is that a uranium glaze with metal in it is no different than any other glaze that you put in. And I put in lots of glazed things in the microwave, and it's never worked. It does not like spoons. It does not like forks. I've demonstrated that as well, but I would guess this glaze and its color is no less or more friendly to microwaves than any other. You know, we have glazes that have iron in them. That would be my guess. Has anybody done the experiment? Plates don't, I mean, microwaves and plates don't get along all that well either. So they do warn about cobalt glaze because they may have more cobalt than the microwave. The issue here is metals in a microwave oven, that they cause arcing and sparking and burning out of the klystron, and again, the tubes don't like that. Have you ever fried a grape in a microwave oven? That's we'll talk about grapes in microwave ovens too.
Why is there a limit of 92 atomic number identifying uranium to naturally occurring elements?
Say your question again.
Uranium is the heaviest naturally occurring element.
Oh.
Why is there a limit of 92? I mean, there has a question to do with stability above that.
Let me say two things, and somebody may want to add in on that. I think long, long ago on our planet, there actually were elements heavier than uranium. And what happened is they had shorter half-lives and they decayed. So 92 is what we see now because it has the longest half-life. There will be a time when there's no uranium on the planet. You're not going to be alive, I'm not going to be alive. We'll be lucky if our planet is alive after about 10 half-lives. Half of a half of a half of a half of a half gets to vanishingly small. So the first thing I want to say, there probably were the other elements. The second thing is that the people who study nuclear stability, and I'm not one of them, talk about what makes a nucleus stable, and it's a combination of how many this is, how many that's, magic numbers they call them. And in terms of what works, uranium apparently has a combination that works. So does going way out as an element, somebody help me, element 114? That they're looking at as being an island of stability, that they're expecting that one to be, I see a head nodding, thank you, stable as well. So some of this is just looking at the nucleuses, making up theories of how many neutrons and protons in there are stable and not, and I will just hand wave at this time and say uranium is. What I think is also interesting is how you decide how nature knows what an alpha emitter is and what a beta emitter is, and why some may even do both. And I'm not good at explaining that one either, is to look at something and a priori decide, is it going to be an alpha, beta? I mean, I know if it's heavy, it's one or the other. And if it's neutron rich, it's likely beta minus, and if it's neutron short, it's beta plus. But how it even decides how it's going to decay, I find that a very interesting one too. And maybe a nuclear you have something you want to say about 92? The hand wave, thank you. Good enough hand waving? Good question.
Any other questions?
That one right there, I see it.
You're like Jerry
With a
Springer.
little help from Brenda.
You're getting good exercise. When you buy a house, you do the radon test, and you're supposed to be less than 2 picocuries or something like that. What is your opinion of how they came up with that limit as to what's healthy and what's not?
Good question. The most comprehensive study I know of radon, and the EPA, I don't know if it's the EPA that sets this one, they set every other limit, so I assume they set this one too, is 4 picocuries and up is too much, and 4 and below is safe. And that isn't all that different than the National Ambient Air Quality Standards. 9 parts per million carbon monoxide is the break point. They decided 10 is dangerous and 8 is okay. So the EPA is very familiar with setting these things somewhere. Now, how they actually set it, the only evidence that I know that has been used quite a bit is the National Longitudinal Radon Study in the state of Iowa, where there are very high levels of radon compared to some other states. And I'm not sure why Iowa landed in the wrong square on the game board. But they looked at, also people in Iowa tended to live in one place for a long time, so they could measure generations of families and then measure where they lived. And my guess is that the data that they came up with came in that manner of knowing people who had lived there for a long time, knowing what the radon levels were, extrapolating back and assuming they were similar if they hadn't changed their kind of basement, and then said that, like any epidemiological study, this number seems okay, you get here, the rate is unacceptable. Go ahead, take it, Ed.
Yeah, I have a question about the radon in the house.
But let
Okay.
me be sure, does that give you something to go on? Because I don't know the real answer, but I'm telling you what I do know about related stuff. The short answer would be they made it up. But they made it the best guess that they could based on the evidence. And that's very much like the National Ambient Air Quality Standards. Above this level, people are affected. Looking at large numbers of people. Ed?
Yeah, this is a kind of low quality science question. So when I bought my last house, we looked at two houses, and one was a modern house, and it had, we did the radon thing. They put the little can with the holes, and they came back, oh, you're going to need to do these things.
Remediation.
And then we had the house that we eventually bought, which was old and big and kind of drafty and lousy. And that one was in the same vicinity, and, oh, this is great, no radon and all this. So the issue, like in the house I bought with busted out basement windows and lots of ventilation, is it the same thing with your Geiger counter? Is that, in other words, is there like venting and things that are letting radon go out? In other words, is how we construct houses connected to
Yes.
radon?
For example, Puerto Rico is a volcanic island, and you would expect the houses to have incredibly high radon levels based on the amount of uranium in the soils and the subsoils. Now, why isn't radon a problem in Puerto Rico? Two reasons. How do they build a lot of their houses? Right, concrete slabs. Second, do they weather strip them in Puerto Rico? Only with a hurricane might they try to board the thing up. But their houses are open to the breezes. So one is they have a concrete slab they build on, and two, they let the breezes in and out, because that is a good thing to do. Take the Minnesota house. Do we weather strip it? You bet. But, like, I have a farmhouse that had a sand basement. So the type of basement determined how much could get up. And then depending on what came through, depending on how leaky, drafty, uncaulked whatever your house is. So part of it is what's in the soil underneath. Part of it is how you construct the house. And part of it is dumb luck in the sense that you can have one house next to another house. This one has 10 picocuries, and right next door you've got 1 picocurie. Depends on the fracturing in the rocks down below. So just because your neighbor's okay doesn't mean you're okay. A lot of things. Yeah, the question here. 2 questions.
Is it possible to actually pull out a neutron or a proton on an atom without splitting it to form another atom?
Only on paper.
Or
I
is
think-
the force too great to...
My students have always wanted to have neutrons in a bottle. In fact, I think a lot of people have wanted to have neutrons in a bottle so they could play with them and do things with them. And you are absolutely right that neutrons by themselves don't last. Actually, they don't last very long. They decay into a proton and an electron. But a quick answer to your question is, as much as we'd like to have an atomic tweezers, so far we don't have one. Would we like it? Yes.
But if we could...
If
but
we
if
could.
we, yeah, could
If
we
we-
pull it out with...
Without splitting it?
Or would the force be too great? Or would we split it? I mean...
The part I can tell you about splitting is it would depend what you pulled out of what. For example, in uranium-92, you could probably happily pull out one of those neutrons, and who would care? There are, how many of them, 100 and something neutrons in there? You're talking about one of the little atoms, and you pull one out, and you may then upset the nucleus and make it unstable. So in part, the bigger elements have neutrons to spare, and the little ones are a lot shorter on their neutrons. Get that man an atomic tweezer, yeah.
Since alpha decay in itself isn't that harmful to the body, what part of radioactive decay is harmful?
Okay.
for that?
Alpha decay is harmful if it's in the wrong place. And the model I'll give you is, you've heard of DNA. It's this long molecule that's built like a ladder and it's got a twist in it. If you have a radioactive substance, the odds are whatever it emits, a beta particle, an alpha particle, it's not going to hit your DNA, it's going to hit your water because you're mostly water. So what happens is that often the radioactivity will ionize the water, and that's what I was talking about, this strange species, not H3O+, which some of you may know and love. Actually water, H2O+, with an electron that's been knocked out. That immediately reacts with water, and if it happens to be around DNA, it may break one of the strands. The good thing is, as you've been sitting here, your strand's been breaking and your body's been repairing them on a regular basis. Your body knows how to deal with one strand that's broken and repair it in a matter of hours. See if there are any biochemists who would say that better. If it happens to break both strands, you've got maybe one of three scenarios. One is the thing just in its process of that dies. It goes away, it's not going to mutate, it's not going to cause a problem. It may recombine twisted, it may recombine with another piece, it may recombine backwards, it may do some gene splicing that you didn't intend. Most of that too, your body it's not going to function, it's not viable. It's the one that may live and go and be reproduced onward that may cause some trouble. In particular, alpha radiation, beta radiation, gamma radiation, cosmic rays, all of these can produce things that may make little cuts in your DNA. Most of the time, your body handles them. Sometimes it doesn't. Those of you who know and study cancer, with each cancer patient, it's all or nothing. It's not that it's a probability. I mean, they're going to live or they're going to die. And I think I can say this honestly, that there's probably nobody in here who doesn't know somebody or hasn't faced it themselves where something got going wrong. And then it's all or nothing. That person's going to live or that person's going to die. Did that answer your question about the different types and where it gets into trouble is especially when it gets interacting with the genetic material? And most of it our bodies are well equipped to deal with, but not always. Too much radiation is not a good thing.
Any other questions? If not, if you just allow me one moment, Kathy, on behalf of all of us, I want to say thank you. And as it's a tradition with the Squibb Lecture Series that we would like to present you with this plaque. It says the S. Dexter Squibb Lecture Series in Chemistry, 2005, Catherine H. Middlecamp, University of Wisconsin-Madison, Chemistry in Context. We will take home and remember your visit with us for a long time, and this is just to help you remember us, and we very much appreciate you coming and spending time with us. Thank you very much.
My pleasure, and does it fluoresce?